Okay, so second statistic or second parameter that we need to look at is population mean. Okay, and with that we have a very important theorem that we need to consider as well. Okay, population mean given by the symbol mu kind of looks like a U, little tail on it at the start. Okay, sample mean also relevant to us, x bar. Okay, x with the little line over it. Population standard deviation represented by sigma, the little kind of O shape, and then sample standard deviation represented by S here. Okay, as with population proportion, calculating population mean can be very difficult. Okay, and I'm conscious as well. You could be watching this having not watched population proportion, so we shouldn't timeline these things. So what we're saying here basically is that population mean is very difficult to calculate because that would require me to ask every single person in the entire population, and if that was, for example, the average result of a Leaving Cert student in a particular subject, it's not feasible to ask every single Leaving Cert student in the country. So what I would probably do instead is ask a sample. I would pick a smaller group, I would pick a kind of school or collection of schools within a certain area, or I might pick schools across the country, and I would use this then as a representation of the actual population. Okay. What I might do to make that more accurate is take a certain number of take a certain sample size and then take a number of samples of this size from different places. So I might look at taking 30 people from loads of different schools and samples of keeping the size the same, but taking all of these samples from different places or from kind of different groups within places and that sort of thing, and I might get the sample mean and the standard deviation for each of these samples. Okay, this will form what we call the sampling distribution of the mean. So you're basically thinking about here, I'm taking all these values, I'm representing them in nearly that histogram idea. So I'm kind of putting in, how many times each of my sample means appears and kind of getting some sort of representation for that. And these will approximate a normal distribution if the sample size is large enough. And I suppose that's what's important here, is that the sample size must be large enough for this to approximate a normal mean. And you can kind of see the example here in the little diagram here. So if we start with a normal distribution, then no matter the sample size, it remains normal. If the distribution I start with is slightly skewed, then as the sample size gets bigger, we get that more of a normal curve. Okay, we see it even more with the irregular shape there at the end, how as the sample size gets bigger, it gets much more normal. Okay, but 30 is kind of the magic number here. Okay, we need samples to be at least 30 or bigger in order to be sure that this theorem will apply and that this sampling distribution will be normally distributed. And this leads us to, I suppose, what we call the central limit theorem. So the idea with this is that if a population is normally distributed, the sampling distribution of the sample means is also normally distributed. Okay, so I suppose basically here, if the parent distribution is kind of what we mean by that. So I can put that here, so maybe the parent distribution. What I mean by that is if we're told that something is normally distributed and then I take a sample from it, no matter what size the sample is, that will also be normally distributed. Okay, so that's kind of the straightforward one. That's the ideal scenario, if you like. If not, we need a large enough sample, bigger than 30, then that will be normally distributed, no matter what the original distribution was. So that can sometimes be a question of why are we sure that this works, and that's why. Okay, because the sample size might be of a certain size there. The mean of the sampling distribution, so we're thinking there mu of x bar, okay, the mean of the sample means, will be the same as the population mean. Okay, the idea here, I suppose, is if I take loads and loads and loads of samples and then get the average of those, then the average of that distribution, the mean of that distribution, ideally, I mean, that's kind of the goal, would be that it would approximate or be the same as the actual population mean. Okay, and you kind of, again, kind of logically does make sense to us that if we think if I was to ask loads of people and get all of those mean values, then at some point, okay, if I have big enough samples and I've taken enough and all of this, at some point then the mean of those sample means should be the population mean. Okay, or should be kind of identical. So that's the idea there. The standard deviation, however, is not identical to the population standard deviation. It does account for the samples. Okay, so it accounts for the fact that samples were used, which is kind of where the square root n comes in at the bottom there. And this is often called the standard error of the mean. And it's called that in many places, including the formula and tables book. Okay, so that's kind of why we need to know the notation or the definition there. So the standard error of the mean, that's going to be your standard deviation for your sample means. It's how far I would expect a sample mean to be from the actual population mean. Okay, so it kind of falls into a similar idea to kind of your z-scores, which is what we're going to be looking at. But just that idea that standard error for sample means slightly different, obviously, to just the standard deviation itself from the actual mean value. Okay, it has that square root of n, which accounts for the fact that we're working with samples here. So obviously that brings us then to this idea of z-scores for sample means. So if I have a certain distribution and I maybe know what the population mean is, and then I'm taking loads of samples, I might want to know what's the probability that a sample would have a certain mean, or would have a mean bigger than a certain mean, or smaller than a certain mean, okay, relative to the actual population mean. Okay, so we're kind of looking at, right, I know that the population has a mean value of 70, but if I take a sample here, what's the chances that that sample would have a mean that is bigger than 72? Okay, or smaller than 63. We might want to look at kind of those comparisons here. Okay, and the questions, obviously the wording and the idea here is very reminiscent of our usual z-score ones, where we're trying to compare maybe a certain value comparative to the distribution itself. Okay, and we might want to look at the number of standard deviations and how far is that value away from the average value or the mean or central value here. But rather than looking at specific values here, we're looking at the sample means and how far away is this mean value from the actual mean value. So rather than looking at how far is a particular value from kind of the distribution mean value, from kind of the average value of the distribution, we're looking at how far is the sample mean away from the actual population mean. Okay, and I suppose the slight difference for that again is the fact that it's a sample. So it's very similar to our z-score, our standardizing formula. The differences, I suppose, are the x bar here in place of x and the sigma x bar. Okay, the fact that it's sigma over root n as opposed to just sigma itself. Okay, this is called the z-test, okay, which we will use in hypothesis testing. But just to remember that that's what you're looking for. It's the one sample z-test for sample means is what you're looking for. It is in your formula and tables book. You just need to look out for it. The key things here I would say to you is if there's mention of samples, then you're looking for this one. Know what your letters mean. Okay, I know it kind of seems like I'm dwelling on this idea of kind of all of these individual letters and kind of what do they stand for, but it's important to have an idea of what all the letters mean, because it's only through that that you're going to know if you're using the right formula or not. So here, for example, knowing that x bar is a sample mean, so if the question just says Johnny scored 7, then that's not a mean value, so this wouldn't make sense to use there. Whereas if it's here, it's like, what's the probability the sample height is greater than this, then that's going to be using this formula here. So you look at what you have in the formula. If there's mention of sample, you're going towards this one. But let's see how this applies, I suppose, in some actual questions here. So looking at the z-test for sample means. The average height of adult men is 175 centimeters, so that's a mean height, with a standard deviation of 8. A random sample of 36 men is selected and the mean height of the sample is measured. What is the probability that the sample mean height is greater than 177? So let's lay out everything that we know here. The mean height is 175. The standard deviation is 8. The sample that I've taken is of 36 people, and we want to measure x bar being greater than 177. Okay, so the question here is, what is the probability that x bar, that the sample mean, is bigger than 177? Okay, so let's have a look. We're going to convert that to a z-score, x bar minus mu over sigma over root n. Let's fill in all of these values. 177 minus 175, 8 over root 36. So we know here we're looking at above average, 177, so it's slightly above average. Root 36, 1.5. So I am looking here for the probability that z is greater than 1.5. Okay, if I look at this using one of my quick little sketches here, I'm basically looking for this region here to the right hand side of 1.5, and we should hopefully remember from our work on z-scores that that is the same as 1 minus the probability that z is less than 1.5. So basically all of this region that I'm shading in black here corresponds with less than 1.5. The region we aim for that's the kind of region that I'm allowed to use with my z-scores. Now let me see, we had the z-score formulas the last day, so where are they gone? Here, so we're looking for 1.5, so let's just read it from here, I suppose. So 1.5 here is 0.9332. Okay, 0.9332. So let's fill that into our question here. So we're doing 1 minus 0.9332, which gives me a very small chance, 0.0668. Okay, converting that maybe to a percentage, that gives me a 6.68% chance that somebody, or that a sample mean, has a height greater than 177. Okay, and that seems kind of realistic. There's only about a 7% chance that if I take a sample of 36 men, that the average height in that sample is 2 centimeters above average for the whole group of people. Okay, that kind of does seem reasonable there. Within that I get an average value of 36 being 2 centimeters above average. Yeah, seems kind of reasonable there. It's not impossible, but it's just unlikely. Okay, we look at some practice questions here then using my z-test for sample means. So a normal distribution has a mean of 80 and a standard deviation of 8. A sample of size n isn't selected at random and the mean of the sample is x bar. Find n if the probability that x bar is greater than 82 is 0.1977. Okay, so we're immediately maybe jumping into some of these slightly more awkward z-score questions, but let's have a look at it. So we're basically saying the probability that z is greater than some particular z-score value is 0.1977, which means the probability that it is less than this z-score value is 1 minus 0.1977, which is what? 0.8023. Okay, so we'll go and see where in my z-scores that value lines up. Okay, all the way up here, 0.8023. I can see it here. That lines up with 0.85. Okay, 0.85. So we're basically saying here that there's some sort of value up here. The probability that I am to the right of this is 0.1977. So the probability that I'm here is 0.8023. Again, the reason that's useful is that's what I can read from the log tables. So that means my z-score value is 0.85. I know here as well that the mean is 80, and I'm looking at what's the probability that something is above average, above the mean. So I am expecting a positive z value there. So that's why I'm quite content to say that my z-score value there is to the right of the middle value. Okay, so looking then at calculating the actual value here, z is equal to x bar minus mu over sigma over root n. We'll fill in some of these values. So we know what the z value is here is 0.85. My x bar value, I don't know. My actual mean is 80, my standard deviation is 8, and my sample of size n was... we're saying that x bar is greater than 82. So we'll include that here, of course. And we're looking for the sample of size n, root n. Okay, so let's kind of continue working out this value here for ourselves. So 0.85 is equal to 2 over 8 over root n. Okay, doing a little bit of rearranging here. From my work on fractions, we should remember that this can be written as 2 root n over 8. 0.85 times 8 is 6.8. So 6.8 equals 2 root n. 3.4 equals root n, which means n is 3.4 squared, 11.56, which means I would need a sample of size 12 to be sure that the mean of the sample is bigger than 82. Okay, so if the probability that the sample is bigger than, that the mean of the sample is bigger than 82, I would need a sample of at least 12 there. Okay, we'll look at one more example. A population is normally distributed with a mean of 12, standard deviation of 3. Find the sample size. We're looking for sample size again. same thing again, where x bar is the sample mean. So we'll fly through this one, same idea again. The probability that Z is bigger than some particular value is 0.05, which means the probability that it is less than that value is 0.95. Okay, that is going to give me a z-score value of 1.65. So we basically have here that 12.5 minus 12 over 3 over root n is equal to 1.65. We have 0.5 root n over 3 equals 1.65. And we're basically following kind of the same playbook here as we just did. 0.5 root n equals 4.95. Root n equals that divided by 0.5, which is 9.9. And n is 9.9 squared, which is 98.01, which would mean we would have to go up to 99 people to be sure. Okay, it's because 98 is not enough. We have to go to 98.01, so we have to go to 99 people because we can't have fractions of people. Okay, I think we're going to pause that one there for a moment. I'm going to continue then looking at population mean and standard and confidence intervals in the next one. But if all we take from this, first of all, is just that idea of the central limit theorem. So the idea that if I start with a normal distribution, then no matter what samples I take, they'll be normally distributed, or the sampling distribution will be normally distributed. If the sample size is large enough, then it doesn't matter what the original distribution was, that sampling distribution will still be normally distributed, so I can still apply a lot of my work on normal distribution here. The mean of the sampling distribution, so the mean of the sample means, will be the population mean, but the standard deviation or the standard error of the population of the sample means will be sigma over root n. Okay, with the root n there kind of accounting for the sample. And then that idea as well of that z-test statistic, which is used in hypothesis testing, so you'll see more of it in that later section, but knowing that we use that when we're looking to compare sample means and their values or their probabilities, or the probability of achieving a particular sample mean or a mean larger or smaller than a particular sample mean for a given distribution.